Welcome to our first screencast for our physics units. Make sure that you have your volume up loud enough that you can hear all the examples. You'll want to know more than just what is on the screen. Also, please remember to take notes on your note sheet as you watch this. If this is for homework, do not let anyone copy your notes. That'd be an honor code violation. Make sure that you do not copy anyone's notes either. Now, on to our lesson. So this lesson is primarily about speed and velocity. But before we talk about those two topics, we need to make sure you know what motion is. You're probably thinking, of course I know what motion is. And you're right. I see that cat, in the bottom here. Let's get him moving. There we go. So I see that cat moving. I know what motion is. Exactly. Well, how do you know that he's moving? Well, maybe you're comparing him to that cabinet in the background, or maybe this part of the wall here. Maybe you're comparing him to that crack. And that's really kind of how we start to see what motion is. We're comparing it to a reference point. So our definition of motion is that when an object changes position over time relative to a reference point. And again, that reference point is just something we're using to compare the object to, like the door, that part of the wall, the cabinet. We're using something to show that, oh, the cat was on this side, now it's on this side, so the cat's in motion. There's a little cartoon here. I don't know if you can see it. It's a little more boring than the cat moving, maybe. But it talked about this guy named Barry. So he's on the left side of the sink. Now he's on the right side of the sink. So we could tell that he's moving because we used that sink as a reference point. But you could use one of these other things as well. So pretty simple idea. One last little point with this, though. Does the reference point have to be standing still? So in these examples, whether it's the sink or the toilet or the cabinet or the wall or the door, those are all staying still. Does the reference point have to stay still? No. Let's say that I was running with this cat here, and the cat blew by me. I could tell if the cat was going faster than me, or you could tell the cat was going faster than me by using me as a reference point. So even though I was moving, you could still use me as a reference point. Or maybe you're watching like a NASCAR race, and you see one car going past another one. You know that car is going faster compared to the other car. You're using the other car as the reference point. So the reference point can be standing still, like in these examples, or the reference point could be moving. And then kind of one last point about study with a reference point. I've had this happen to me, maybe you have too, where I'm like in an airplane or maybe one of those big coach buses and like the fans are going and it's kind of all this floaty feeling. And you look out the window and you see another plane or another bus and they start moving. But because you got the air conditioning, the fans and stuff going, you can't tell if you're going forward or they're going backwards. It's kind of this really weird feeling. And it's because you don't have a reference point. So that's it for the reference point. Now we're going to get on to our main lesson, which is speed and velocity. And you might be thinking that, I know what speed is also. It's how fast something's going. Yeah, exactly. Okay, speed is how fast something's going. We get our kind of official definition here. That speed is the distance traveled by an object per unit of time taken to travel that distance. So yes, it's how fast something is going. Well, the units, we'll look at our definition again. It was the distance traveled per unit of time. So our units are going to be a distance measurement over a time measurement. So an example might be meters per second, or maybe you could do another example that was kilometers per hour, maybe. Or maybe if you miles per hour. So some kind of a distance measurement over a time measurement. That's how fast something's going. So we'll get right into examples here because again, I think you know what it is. So I said most objects do not travel at a constant speed. To find the average speed, just divide total distance by total time. So this is different than like an instantaneous speed. I'll talk more about that in a little bit. So that's why it says, average speed here. Again, our formula is speed equals distance over time. Do some examples. My cat ran 40 meters in 5 seconds. What's his speed? So speed equals distance over time. So speed equals 40 meters divided by 5 seconds. Multiply that out and you get 8 meters per second. My cat was 8 meters per second. Seems pretty quick. I think probably accurate. Another example, Kira jogs to a store 72 meters away in 36 seconds. What's her average speed? So again, speed equals distance over time. So speed equals 72 meters over 36 seconds. It's going to give us 2 meters per second. So she is quite a bit slower than my cat is. What if you traveled 7.5 kilometers in 1.5 hours? So again, speed equals distance over time. So speed equals 7.5 kilometers over 1.5 hours. Divide that out, and I get 5 kilometers per hour. So that's average speed calculation. Now remember, I said average speed, instantaneous speed. As that cat's running, or as Kira's jogging, she's probably not going 2 meters per second that whole way. She'd slow down, she'd speed up. Okay, so this is an average speed. And the graph on the next slide here gets to this average speed idea. So we see in the graph, we have a blue line is actual, and then average is the red. So if we look at this person's actual speed, or this car, or whatever it is, so looking at the blue first, goes from about 0 distance at 0 time to about 90 kilometers in 1 hour. So for that first block there, 90 kilometers per hour for that first block of time. Second block was going from 90 up to, it looks like, let's say 210. So 210 minus 90, that'd be what, 110? So 110 kilometers per hour for that next block of time. The next block of time from 2 hours to 3 hours, looks like we have, what I say that was 210 up to like 300. So now we subtract again, we get back to 90, kilometers per hour. So this, whatever, car, train, whatever it is not traveling a constant speed. We're just kind of finding the average. So let's ignore this last block for the moment. You could calculate that too. But if we look at the whole thing now, we see that it went, let's say that's 360 there maybe. Okay, follow it over. So let's say 360 kilometers in 4 hours. So that, whatever it is, averaged 90 kilometers per hour for the trip. Okay, that's this idea of average speed. It's not the instantaneous speed. They may be going faster, they may be going slower, but it averages out to whatever the speed is that we found. So that's our speed part of this topic. Now we're going to move on to velocity. And velocity is very, very similar. So we started with an example. I said, imagine that 2 birds leave the same tree at the same time. They both fly at 10 kilometers per hour for 5 minutes, 12 kilometers per hour for 8 minutes, and 5 kilometers per hour for 10 minutes. Let's say they don't end up in the same place. Why don't they end up in the same place? Well, they're birds. They're flying. They're not taking a road or something like that. They're probably going different directions. And that's the key with velocity. Direction matters. So velocity is just the speed of an object in a certain direction. So fairly simple, speed in a certain direction. So our formula is the same, except now I have a V for velocity instead of an S for speed. But it's really the same formula that we just did, but don't forget to add the direction. You have to add the direction for these. So more examples. Now we have a bus traveling 20 kilometers south in 2 hours. What's its velocity? So velocity equals distance over time. So velocity equals 20 kilometers over 2 hours. That would be 10 kilometers per hour. Now I have to add my direction, south. So again, fairly simple. You're just doing your speed formula, but adding your direction. So velocity depends on both speed and direction. So velocity is constant only if they both do not change. A change in either changes velocity. So we had that bus was going 10 kilometers per hour south. So what if it continues to travel at 10 kilometers per hour, but now it turns right? So the same speed, but it's turning right. Does the velocity change? So the answer is yes, because the direction changed, okay? Speed and direction go into velocity. So now we have President Clinton. He used to be a big jogger, so I used a picture of him. So I said President Clinton jogged 8 kilometers north in 2 hours. What was his velocity? So again, velocity equals distance over time. Velocity equals 8 kilometers over 2 hours, which will give us 4 kilometers per hour. And what do I have to do? I have to get our direction. What was it? North. Okay, so President Clinton jogged 4 kilometers per hour north. Now, I'm used to kind of the English system or imperial system. I don't really know what 4 kilometers per hour means, maybe. Let's convert that to meters per second to get a little bit better understanding of, what kilometers per hour means. So what I'm going to do is I've got my answer from over here. So I have 4 kilometers per hour here. I'm going to convert it to meters per second. So I'm going to do what's called dimensional analysis. So I look at it, and what I need to do is I have kilometers at the top, and I need to get rid of that and get meters in its place. So I want to get rid of the kilometers, so I'm going to have on the bottom kilometers, so it'll cancel out, and meters at the top, because that's what I want. So how many meters in a kilometer? Well, it's 1,000. You remember your conversion table, your King Henry died money drinking chocolate milk kind of thing. So we had 1,000 meters in a kilometer. So we multiply it out, you'll see the kilometers cancel out, and I'm left with 4,000 meters per hour. And again, I'd have north. So I'm closer, but I'm not still at seconds. I want to get to the seconds. So we're going to do the same kind of thing. I'm just going to multiply it. I want to get hours out of the denominator. So I'm going to have hours up here, seconds on the bottom, which is what I want. And in 1 hour, there are how many seconds? 3,600. So I multiply that out, and I get 4,000 kilometers over 3,600 seconds. And that would give me, what would that give me? About 1.1 meters per second. Now, don't forget my direction, north. Okay, so now I have a little bit better understanding. Okay, he's going 1.1 meters per second north. Not very fast. If you didn't quite get how we did this dimensional analysis here, don't worry. We will have lots of practice doing that in the future. Let's do one more example, kind of looking forward to our astronomy. So the moon is 386,000 kilometers from Earth. In 1969, Apollo 11 traveled that distance in about 50 hours. What was the average velocity of Apollo 11? So again, we have our formula, velocity is distance over time. So we're just putting our numbers in. So we had 386,000 kilometers in 50 hours. Divide that out, 7,720 kilometers per hour. Direction, like moonward, I was going to put an up arrow. Okay, so towards the moon. So 7,720 kilometers per hour going towards the moon. Again, let's figure out, okay, what does that mean in like meters per second? So I have a little better understanding of what that means. So we're just going to do the same thing like we did in that last example, our little dimensional analysis. So I had 7,720 kilometers per hour. And I multiplied, remember, I have to get this kilometers out of the numerator. So I'm going to put that in the bottom and replace it with meters, because I want meters as the numerator. And remember that there were 1,000 meters in 1 kilometer. That's going to cancel my kilometers out to leave my meters, so I want. And then also, I had to get rid of that hours in the denominator and replace it with seconds. So I want to get my hours in the numerator, my seconds in the bottom, and That was 1 hour was 3,600. So now again, my hours were canceled there, and I'm left with meters per second as my unit label. So again, we multiply that out, we'd get 7720 times 1,000 or 3,600, and what we get for our answer, you put in your calculator, you get 2,100 meters per second to the moon. So a little bit faster than President Clinton was jogging. Again, if you don't quite get that dimensional analysis, we will practice more of that during class. The last part of this lesson on velocity is with combining velocities. Our video is 15 minutes long here, so we're going to skip this for now. We'll do this in a separate lesson. You don't need to have this long of a lesson for this unit. Thank you very much. We'll get that next lesson next.